Okay, welcome back. So this is video 2 for Thursday, August 22nd. We are going to pick up where we left off. I want to give you a heads up. I'm going through the slides, and as I mentioned at the beginning of the first video, these are slides that have been prepared over the years. I'm adapting them to this course and making some changes. Because of timing and travel and so forth, I had less time to change the slides than I would have liked. And so we are going to be jumping around a bit. Let me share my screen here. Okay, so you should be seeing my screen. I'm using for now, I'm talking about the numbers here at the bottom of the slide. So currently I'm talking about slide 40. This might not actually correspond to the page numbers of the PDF if you print that off. In this video, my plan is to talk about, let me try this. Maybe this will be a little bit more legible. I'm going to talk about slides 40 and 41. I'm going to drop back and then talk about slides 30 and 30 through 32. And then I'm going to talk about 28, 29, and 33 and 34. So here, this is just going to summarize the Gauss-Markov simple linear model. This is going to be sort of an estimation preview, looking at the Galton data. And then this is going to be talking, it's almost an aside, but it's going to talk about linear models and kind of contrast what's statistically linear and nonlinear. So be aware that I'm going to be jumping around a bit through this presentation. Okay, so slides 40 and 41 can be seen as a review of what we covered at the end of the previous video. We introduced the Gauss-Markov simple linear model. Yi is the response for observation I. Xi is the predictor variable for observation I. Xi is not random. The randomness arises only from the error term, which is anything that's not explained by the deterministic piece, beta naught plus beta 1 times xi. If on the exam I say write down the Gauss-Markov simple linear model and you write this down, you'll get less than half credit because that is not the model. The model requires us to describe the assumptions on the random part, epsilon I. So remember, epsilon I is random. We're thinking about it having a distribution, but that doesn't mean we have to describe the distribution completely. The philosophy behind the Gauss-Markov simple linear model is we're going to make the bare bones assumptions necessary. And so we assume that the error term has mean 0. So the way to think about that is there's a distribution and it's centered at 0, center being described by the mean, but doesn't mean it's symmetric, doesn't mean it's Gaussian or normal. The variance of epsilon I is sigma squared. And importantly, we said that there's no I attached to the sigma squared. And so in that assumption, that says that the error terms for observation 1, observation 2, and observation 3 all have the same variance. It doesn't even say that they all have the same distribution. So we could think of symmetric distribution for the error in associated with observation 1. We could think of a non-symmetric distribution associated with observation 2. They both have to be mean 0. They both have to say the same variance, but it doesn't say that they have the same distribution. Finally, we say that the error terms are uncorrelated. That's a step weaker than saying that they're independent, but we can get away with it. So in that philosophy of thinking about this model being bare bones, we're going to make the simplest assumptions we can get away with just saying that they're uncorrelated and not say anything else. So notably, we don't say the errors are IID, independent and identically distributed. So slide 41 basically is summarizing what we did. What distributional assumptions are made? Basically, we're assuming that no distributional assumptions are being made. We are assuming that it's mean zero, that it has a common variance, but we don't specify Gaussian. We don't specify normal. Gaussian and normal are synonymous. If you're unfamiliar with Gauss, the term Gaussian, the Gauss distribution is what is often referred to as the normal distribution. So get used to those equivalent terms. What is fixed? Well, beta naught is fixed, beta 1 is fixed. We don't know them as statisticians, but we are assuming that there are true values out there and they are non-random. What is random? The epsilon i's are random. They have a distribution. We talked about the properties of their distribution. The yi's are random. And we were able to say a bit about the yi's because starting with the assumptions on the epsilon i's. For instance, we said that the expected value of the yi's is given by this term here, where the xi is where this is the deterministic part. What is unknown? Beta naught is unknown. Beta 1 is unknown. I'm going to go ahead and throw xi up here as being fixed. It's not random, but it is known, so it's different. We're going to assume that for every observation we see its predictor variable, and that predictor variable is fixed. What is observed? Well, we observe the xi, we observe the yi, we do not observe the epsilon I. And as we said, the beta naught and the beta 1 are unknown. Okay, so that summarizes what we know about the Gauss-Markov simple linear model. Let me jump back now to slide 30. Okay, so simple linear regression estimation in R. This is a preview or foreshadowing. So let me write that. Supposed to be a W on the end. So what do I mean by this as a preview? We haven't yet talked about what we mean by estimation for the simple linear regression model. If you put this code into R, which if I were teaching this live in class, I would do, but here is the code if you want to do it. The data set, the Galton data set has been loaded or is available on Canvas, so I'd encourage you to go ahead and run this code. But what we're going to do is we're going to use the LM term. LM stands for linear model. The way the syntax works for this function is that here's our response variable. This means you can think of this as described as or is related to. This is our predictor. So let me write that. This is response. This is predictor. And then the data set is the Galton data set. So what we're doing is we are going to run this LM function, this linear model function. This is an arrow, and it's going to get stored in this R object called fit. And then if I simply type fit, R is going to respond with this response here. It's going to spit this out. It's going to tell, all it's doing is it's saying what was the call, what was the command used to create this R object called fit. And then here are our parameter estimates. This is beta naught hat. This is beta 1 hat. A note about notation. So beta naught and beta 1 are the true values. They live happily in math land. We don't know them, but we think that there are true values out there, and they're not random, they're just unknown to us. What we're going to do is we're going to use data to estimate beta naught and beta 1. And so we have estimates beta naught hat, beta 1 hat. I'm going to write estimates, estimators. These are the estimates that come out, beta naught and beta 1. So what we're seeing is that the intercept is 22.153. What that means, remember, we interpreted the beta naught on the other slides. That says if x1 were 0, we would expect the value of the response y1 to be 22.15. Or another way of saying that, I've used the word expect, and don't miss that. That has a very specific connotation, expectation. The mean response for xi equals 0 would be 22.15. Now, in the context of our problem, that doesn't make any sense. Really, it's not a meaningful number because the mean parent height is not going to be 0. We don't expect that to actually be describing the data. However, our model needs, we're going to draw a line that's shown here very shortly. Here is our line of best fit. It has, if I continue down this direction here to where x equals 0, notice that x is, the smallest values are, in the 60s. But if we were to continue this line down to 0, it would cross at a height of 22.15. The slope for every unit increase, so let's see, this is about 1 unit over, that's supposed to be a triangle. We're seeing an increase of about 0.6 or 0.67. And so that is beta 1 hat. So these are the estimates. This number was meaningful to Galton. This was what gave him that negative terminology of regression toward mediocrity, basically because this is less than 1. He said, well, tall parents tend to have tall children, but the children do not tend to be as tall as the parents. Because that slope is less than 1. Let's see. What else do I want to say about this? Okay, I started to talk about notation. One bit about notation. The KNNL book use small b1 and small b2 as the estimates for the true values, beta naught and beta 1. I don't like this notation. The slides do not use this notation. The notation used by KNNL is unusual, despite the KNNL book being kind of ubiquitous. So we are going to generally use this notation here of the beta naught hat and the beta 1 hats through the notes. But you may need to do some translation between the notation and the notes and the book. Finally, let me talk about this, estimates and estimators. Whoop. I said that these guys are the estimates. Estimates are beta naught and beta 1 after you've observed the data. We put the data into something, we came out with these estimates, and we come up with numbers. And so they are after we're given the data. The estimator is the formula which goes in, which is used to calculate these estimates. And the important part is that formula, basically think of it as a function. It's a function that you put in the data and it spits out an estimate. Well, the data that we're putting in is random. Those are going to be realizations from random variables y. And so the estimators are also randoms. Functions of random variables are random. And so we have to live in this dual world where we are thinking about beta naught and beta 1 being random. That means that means they live in math land. That means we can describe their distributions. That's going to be real important to us. We want to describe the uncertainty associated with these guys. So that's estimator. And then once we observe the data, we can crank out and we can get the estimates. Okay, so this can be challenging to new statistics students. This is probably familiar to many of you, but maybe at least it's a good refresher. And if this is new to you, we kind of have to train our mind to have this dual idea going on. All right, finally, hey, let me get back to preview. Why is this a preview? We haven't talked about where these guys come from. We just plugged it into R and it cranked out something. What's being done behind the scenes is least squares estimation. We will talk about least squares estimation, but a way of thinking about the estimates is there is some rule for determining what is the best estimate given the data. And the definition of best can differ. For instance, in this first set of notes, we're going to have two different definitions of best. We're going to have best defined by least squares. That's going to be the Gaussian simple linear model. Another definition of best will be maximum likelihood, and that is we can't get there with the model that we've got because that requires a distributional assumption. So that's with once we throw the normality assumption or onto the epsilons, then we can do maximum likelihood. So another thing to put in your mind if you're new to thinking about things as a statistician is there are different definitions of best. There are different ways you can define estimators. And then one of the things we do a lot of as statisticians is we talk about the properties of the estimators and why one estimator might be viewed superior to another estimator. So that is what is done a lot in a class like Stat 530. Okay, so there was a lot here. We talked about this being a preview because we haven't talked about what is going on behind the scenes. We talked about notation, and we see some R syntax. What comes out from that is our line of best fit, and then we can use a command like this, or we can do something more simple. But if you use this command, which is using some commands from ggplot, if you're unfamiliar with it, what we end up with is that scatter plot that we saw before, and then we are fitting in our line of best fit. So notice that there's this P. If we go back in our slides to where we created that scatter plot, I probably failed to mention this, but notice that what we did in line 1 here was we made this plot using ggplot and we stored it in something called P. And then what we can do using ggplot is we can add things to P. So P plus x x label. This threw on the mean parent height label there, and the height for our vertical axis there. And then by typing P, we get the whole thing. So notice we created it in line 1, we updated P in line 2 by typing this stuff on the right-hand side to P. So P's been overwritten with to be a plot that looks like this. And then what's happening on our command here is we have this thing P stored in R's memory, and we're going to add this line of best fit from our fitted model. So there still remains lots to be done. What was the rule? What was our definition of best used to obtain this? But we'll get to that in the next section. I want to go back and cover some slides that I skipped over. namely slide 28, 29, which I'm going to pair with 30 and 34 because I think they go together. Okay, so this is a way of thinking about our simple linear model. And perhaps more generally, it's a way of thinking about regression. So we have, let me change my color here. We have this expression here. This makes sense to us because when we talked about the expected value of y, when I introduced it using the definition in later slides, we said that the expectation of y is given by beta naught plus beta 1 times xi in that case. The expected value of yi is beta naught plus beta 1 times xi. Now this is saying the expected value of y given x. When I define the Gauss-Markov simple linear model, I said we're going to assume that the x's are fixed, that they are observed, and there is no nothing random about the x's. This is essentially saying the same thing. We could think about x as a random variable, but our model is going to be defined in terms of the conditional value on x. Well, once you conditioned on x, it's not random anymore. You're assuming that you know it. So the notion of y is still being the response. X is the predictor. And the expected value of y given x, this is the mean behavior of y, given that x is known. I'm going to write that mean, let me do that here, so it's a little more legible. Mean behavior of y given x, meaning given x is known. So really our model is conditional on x. Beta naught is the intercept as before. Beta 1 is the slope. Okay, so perhaps you're saying there's nothing really new here. This is also talking about things that we are familiar with. We've already said this, but it is conditional on x, so our model is conditional. We want to understand the uncertainty, so our variance, we can think of the variance of y given x being sigma squared. So this all pairs up exactly with our Gauss-Markov simple linear model that we described before. And then if I jump ahead past the estimation bit, well, I guess I failed to talk about this. Let me do that really quickly. I should have tacked this on to before I started talking about this conditional model on the previous slides. On this slide, if I just type fit, it just gives me this pretty basic information. But of course, there's a lot more information that comes along when we do our estimation procedure. So you can type summary fit. Again, it gives you the call. This is talking about the residuals, which is giving us some information about about the residuals. We'll talk about the difference between the residuals and the errors, but the way you may be familiar with it is the residuals are our best guess of the errors. It's the actual value minus the predicted value for y. We see our estimates, but they're also giving us standard errors, t-values, and they're performing a t-test, which is asking whether they're significantly different from 0. This is the important one to Galton, which says, yes, there is a significant, the beta 1 parameter estimate is significantly different from 0, which means there is a relationship between child height and mean parent height. There's some other stuff that's coming along here. There's this where they're talking about the standard error of the residuals. There's this multiple R² test and adjusted R², and these are all things that we will talk about very soon when we talk about estimation. Okay, so let me go back we were talking about this, thinking about our model being conditional on X. So another parallel way of thinking about our model is conditional on X. And we're interested in estimating beta naught and beta 1. We're interested in estimating sigma squared, which is some of the information given on this slide. And then our slides talk about linear models in general, and it says something that seems strange. It's going to say that here's the simple linear model that we talked about on the previous slide. Here's another model, which instead of being just having linear terms, it adds this quadratic term in X. And we all know that, gosh, this would create something that looks like a parabola, depending on the values of beta naught, beta 1, and beta 2, and that would not seem to be linear in our usual description of being linear. Here is another model that we know that what the log function looks like, and that does not look like a line. And yet, what the notes are going to say is all of these are going to be statistically linear. So a model is said to be linear because the outcome is linear in the regression coefficients. I'm going to throw something in here. I'm going to emphasize that it's statistically linear. So statistically linear doesn't mean that the plot looks like that a meaningful plot looks like a line. It means that these models are linear in the regression coefficients. So what we're doing is we can, if we turn around and think of the X being fixed, this is fixed. I'm taking some linear combination of what I have, my knowledge of X. So I'm taking a beta naught plus a beta 1, and here this is also a linear combination of some variables. I've got a variable X, I've got a variable called X squared. Maybe a different way of thinking about that is X2. X2 is a second variable. It happens to be the squared value of X, but it's a second variable. And I'm doing a linear combination of a constant term, the first variable, and the second variable. Likewise, this is a linear model in terms of what I'm calling statistically linear. This statistically linear is not universally used. My point is that something that is statistically linear doesn't mean that its graph is going to be described by a line. As the definition says here, it's a linear combination of some variables. Here's our variable x2, which just happens to be the log of x. And in general, we'll talk more about matrices soon, but we're talking about x data. Now, keep in mind, we're only talking about the deterministic parts on this slide. We see that we're talking about the deterministic parts because we are only, because on the left-hand side over here, we only are talking about the expected value. So let me just expand on this for a moment. So actually, let me jump ahead to the next slide. The next slide says both of these are linear, statistically linear models. Now, neither of these looks like a line, but we could think of these as being statistically linear. What's going on here? Well, what we have is we've got some variable x, and looks to me like there's kind of some curving behavior, and then we've got this oscillatory behavior. And so what we have is we're saying that the expected value, let me do this in blue just because I don't want to shout at you. The expected value of y given x is equal to, if there's probably a beta naught term, there's a beta 1 term times x1 plus a beta 2 term times, actually I'm not going to call that x1, I'm just going to call that x. There's a beta 2 term times x squared. That's giving us that quadratic, that curving behavior that we've seen. And then there's beta 3 being multiplied by some sine wave. Now this sine wave, you know, looks like it has a period of about 20 and looks like it has an amplitude of, maybe it's got an amplitude of 1, but there is some, we'll say alpha plus, actually not alpha plus, I'll just say alpha sine gamma x. And here, alpha and gamma are different than our regression coefficients, beta naught, beta 1, beta 2, beta 3. To make this a statistically linear problem, alpha and gamma would not be estimated. They'd be known by the researcher. I know that this thing oscillates with a period of 20. I know that this thing oscillates. The sine wave I'm going to build in is going to have some known amplitude. But what I want to do is I want to basically just shift this thing by beta 3. And so another way of thinking of this model equivalently would be beta naught plus beta 1 times x1, where x1 is just given by x. Beta 2 times x2, where x2 is x squared, plus beta 3 times x3, where x3 is this complicated sine function. So let me just add one more thing here. So let's contrast a statistically linear model with a model that I'm going to say is non-linear. So if I say y, or let's use this notation, expected value of y given x equals beta 1 times exp, the exponential function applied to x. Okay, the behavior that we could get here, if this is x down here, here is, here is the exponential function. And if beta 1 were 2, then I would take 2 times this, and I would get something like this. Every value here is double the value there. If I multiply by 1/2, we get something like this. If we multiplied by -1, we would get something like that. But that would be a linear model where our x value is, we're taking the exponential function of that. A nonlinear model would say something like expected value of y given x, I have that wrong, y given x equals exp beta 1 x. Now, again, sort of the base function, if beta 1 is 1, that base function is the same as on the left-hand side. We have a standard exponential function. Now, if beta 1 equals 2, we are going to get something that looks a lot like if beta 1 equaled 2 over there. We'd get something that looks like this, but it's different because we know that by rules of exponentials, exp beta 1 x is equal to exp x to the beta 1. So in fact, instead of being double the value, these would be square the value. Take this value and square it to get that value. If beta 1 were negative, now we're not going to get something that returns negative values. If beta 1 were negative, we get a decreasing exponential function. Importantly, this is not linear. in the regression coefficients. There's no way to write that as regression coefficient times some new value x1. That beta is embedded in this. So that is the difference between a model that is statistically linear and a model that is nonlinear. Okay, so that's the point I wanted to make about 28, about those slides. So really in this video, we've covered 3 ideas. On slides 40 and 41, we reviewed the Gauss-Markov simple linear model. On slides 30 through on slides 30 through 32, we talked about, it was kind of a preview of estimation. And maybe the goal of that was just to solidify in your mind what beta naught and beta 1 are, and also this idea of estimating them. But that's going to be, the estimation is going to be the topic of the next lecture. And finally, we talked about slides 28, 29, 33, and 34. On 28 and 29, we represented our model in a different way. It's a parallel way, it's an equivalent way, but it's a useful way of thinking about our model as a conditional model. So we're talking about y once we conditional on x, sort of once we've observed x, which is exactly what we were saying on in the previous lecture, where we said we're assuming x is fixed. This allows us to really zero in on the relationship of y given x. So it's equivalent, but important. And then then we talked about statistically linear models and how all of these models, because they are, how all of these models, because they can be written as linear combinations in terms of we think of they they're linear in terms of the regression coefficients. What we're doing is we're just replacing this x squared with thinking of it as another variable. So it's linear in the variables, but a meaningful plot may not look linear. And we contrasted statistically linear with a model that might be, this is probably a more useful model, but trying to estimate that guy is going to be very different than estimating a linear model. Okay, so I am going to stop there. This wraps up video 2. Thanks.